So I'm Nick Kruskamp. I'm a graduate student here. And today we have Dr. Birgit Peterson, who is a geographer at the Earth Resources Observation and Science Center, or USGS EROS, in Sioux Falls, South Dakota. Her work centers around fire research, remote sensing, and the applications of some of these technologies in federal systems. So with that, let's take it away.
Thank you. Thanks, Nick. Thanks for the invite. Nick was kind enough to extend the invite to come out here, and also for John for doing and taking care of all the logistics for coming out here, where I really appreciate the weather, because when I left home yesterday it was 5 degrees. Just a little bit about USGS EROS, where we're located, why we're located, and what we do. As Nick said, we are located just outside of Sioux Falls, South Dakota. We're a little about 10 miles north of the city proper. We house the largest civilian archive of images of the Earth's land surface, and that's really basically our bread and butter of what we do there, and that's what we're mostly known for. Most of the research interests, but then also all the work that's done in support of that research and for people beyond the walls of EROS itself, is geared towards land change as our primary focus. That's really what the data are primarily used for, and that's what really drives much of the research and the R&D work that we do within the branch that I work in, which is our Science and Applications branch. EROS has been out in Sioux Falls, or just north of Sioux Falls, since about 1973. It was built there, and to be the archive, to be a downlink center mainly for Landsat data. That is what, again, is our primary bread and butter, is that program. We work closely with NASA in launching those, not necessarily in the launching, but in the running of those programs. After NASA launches the satellites, USGS takes them over in terms of ground operations and data management, and a lot of that is housed and run out of EROS. And right now, a lot of the drive is gearing towards Landsat 9 and getting prepared for that and launch in December of 2020. But my area of interest and the group that I work with deals mainly in wildland fire. And we're looking at various aspects of wildland fire. We do a lot of data production that gears towards understanding the impact of wildfire on the landscape, but also how to help people predict where fire might behave and how we should manage it on that landscape. So we're looking at issues of human safety and resource protection. Definitely the managers that we work with, that's very high priority for them. But then also just general land management. How do we work with and live with fire on the landscape? And how has that attitude towards fire and that management aspect change over time? And how will it continue to change over time? So we're looking at all those different aspects. One question we get asked a lot, so I thought I would flash this even though this isn't necessarily a product we put out there, is just interest in what is happening in terms of fire right now. People sometimes like to know where are fires occurring in the U.S. at any given moment. And the National Interagency Fire Center, NIFC, which is housed in Boise, Idaho, is really the clearinghouse for a lot of this information. Is actually also a user of a lot of the data that we do provide at EROS. So it's publicly available information about past and active fires. People are sometimes interested just to see what's happening, especially people in fire-prone areas like to know, hey, what's going on in my area, my region right now. And people who are visiting those areas or going to be visiting those areas would like to know what the impact is in terms of, say, maybe smoke potential or just other recreational impacts in visiting those areas. So this is current large fire incidents. So this was as of Tuesday, before I left the office on April 3rd. All the incidents, major incidents that are occurring in the United States right now. And I think what sometimes surprises people is how much fire actually happens in this time of the year. You will see that over time, I think this is a nice snapshot because you see a lot is going on in Oklahoma right now, with some down in Florida and some scattered out, but mostly throughout the southern tier of states, southeastern tier of states. As the year progresses, you will see that shift. And you'll see it shift to the west, you'll see it shift to the north, and that's usually a pretty standard process throughout the year. Year to date, we already have over 400,000 acres burned. And this is wildland fire, this is not prescribed fire. So it just kind of gives a good indication of how fire is certainly prevalent in the landscape at all times of the year. It's not just a summer or late summer problem. A little bit else to put things into context is just some wildfire statistics over the last 10 plus years. Last year was our second highest year in terms of acres recorded in recent history. 2 years ago in 2015, that was the actual highest year overall. It's sometimes interesting to note that acres doesn't always necessarily translate to number of fires. You'll notice that there are some years where we've had significantly more fires, but the acreage isn't as high. So this gets to a little bit of how do we tally and how do we account for fire. Do we count in acres? Do we count in number of fires? Certainly matters where those fires occur. It also matters if all those acres are severely burned or just have mild burns on them. So all these things, these statistics help us to a certain extent, and they certainly help explain why our firefighting budget is kind of going through the roof, but it doesn't tell the whole story. So we start adding additional layers of information to that to kind of see what's going on. Kind of like to go over a little bit of history of wildfire in the U.S. because I think there's a perception that it's a fairly recent problem or an issue that people have had to deal with. And that it's also mostly an issue that the Western states have to deal with. But you go back in history a little bit and you see the story's a little bit other than we might expect for right now. In 1825, there was a big fire, the Miramichi Fire, that burned over 3 million acres in Maine and New Brunswick. Something that's often lost in current knowledge, something that unless you're from there, you might not necessarily know. So that's a huge fire, 3 million acres in one fire alone. It was in late summer, early fall, and was largely attributed to logging activities in the area. And there had also been an ongoing drought and high winds at that time, which really precipitated the ignition of the fire, but then also its spreading as far and as wide as it did. In 1871, another major fire, the Peshtigo Fire in Wisconsin. Again, there were prevalent drought conditions over that area at the time. Local logging and agricultural activities are contributed to igniting that fire and setting it off. However, high winds also helped spread it as far as it did. Really only petered out because it hit Green Bay, the actual bay, not the town, but the actual Green Bay. Burned over 1 million acres in Wisconsin and over 1,300 fatalities on one night. That number is probably conservative. There was a fair amount of hunters and trappers who lived in that area who were probably not accounted for, and also native population that was probably not accounted for. So it could very well be that that number should be twice as what it is. There's a reason why this particular fire has kind of not had its place in history as others might. There was another major historical fire that occurred that same night in Midwest US. Anybody? The Great Chicago Fire. And a lot of the conditions that made this fire as bad and severe as it was also contributed to the Great Chicago Fire. High winds, drought, a lot of buildings then were made out of wood. They went up. So then we move on a few years into the future in 1920. They called it the Great Fire, although it was a conglomeration of fires in Montana and Idaho. Again, hot, dry conditions prevalent over the area. Burned over 3 million acres, over 80 fatalities. That logging was a role in that one, but so was the rail traffic. You had coal-fired engines at that time, so fire sparks from that were a major source of fire. This fire, however, had a lot to do, this and others that occurred that same year, had a lot to do with a real shift in the concerted effort on behalf largely of the federal agencies, but also others, in how we deal with fire on the landscape. And this was the idea of complete fire suppression. It's something that's called the 10 a.m. rule. And that was if I find or I see a fire on my lands, it is going to be out by 10 a.m. the next day. So complete fire suppression. And they got really good at it. A lot of the people who went in training as firefighters, that was a goal, and they were very successful in meeting that goal, believe it or not. So it really awakened people to this idea that fire is bad. Actually, not only is fire bad, fire is evil. It's something that we need to eradicate from our landscape. And that was really prevalent in US fire management for the next 70 years, 60, 70 years. And then we had the Yellowstone fires in 1988. I don't know if any people have been out to that area or saw that area shortly after it burned or have been to some of those burned over areas since. But that was another watershed event in terms of fire and fire management in U.S. history. And that started as many smaller fires that then kind of grew into one single fire complex. Again, it was a dry summer. almost 800,000 acres burned in the park, and that's the park alone, so it doesn't account for lands that burned outside of the park. But the impacts of that fire and the effects of that fire, especially monitored in time after the fire event, really led to a questioning of US fire policy, which is that total suppression. People noticed that, lo and behold, even after this really severe fire, the forest recovered. They didn't need people to go in and completely suppress that fire. In fact, many forested areas thrived after that fire went through. There were species that need fire. They're serotinous. They need fire for the seeds to actually sprout and grow. And that really came to light after the Yellowstone fires. And it really led people to think, hey, maybe this idea of total fire suppression isn't what we want to do. But if it isn't what we want to do, how do we manage fire in the landscape, and how do we learn how to deal with it and work with it? Around that same time, or a little bit later, the same kind of realization came in working in Sequoia National Park, where land managers went out and realized, we don't have any little sequoia. What's happening? And again, the sequoia are serotinous. They need that fire to kind of come through and sprout and grow. And then they started introducing some prescribed fire to Sequoia National Forest and realized this is really helping the forest. This is what we want, and it will clear out all that other, the incense cedar, jack pine, everything that's growing in underneath that we really don't want here in this forest type. So those things led to a shift, at least at higher levels, in terms of how are we going to act with fire on the landscape. But that still left a whole open area of how do we deal with it, how do we work with the public to get this into an accepted idea, and what kind of data do land managers need to have in order to make informed decisions. And just to bring one a little bit closer in history and a little bit closer geographically, we also, of course, had the Gatlinburg fire of 2016. Again, drought and high winds. I think it was the third or fourth day is when the fire really grew beyond. It had been fairly well contained. And then the humidity dropped to 17% and the winds picked up on like day 3 to 4. And that's when the fire really took off and made a huge run. And I think there were also recorded wind gusts of over 80 miles per hour during that event, which really drew that fire. 8,000 or roughly 8,000 acres burned. That sounds like a small number compared to some of these millions that we've heard in other fires, but we can't always tally the impact of a fire in terms of acres burned. Again, here we had significant fatalities because of that event. It was also an incident, unlike the others that I've mentioned, and especially the Yellowstone fires in recent history, where we had a significant fire in what we call the urban-wildlife interface, or wildlife-urban interface, where we had people living. It wasn't out in a park somewhere, it was in people's backyards. And how it wasn't a park, but it did spread into people's backyards. And how do we deal with that with fire in the community? And one thing to note is that was actually just one of many fires that was occurring in the area at that time. In western North Carolina, there were 34 fires that occurred that same season, so late summer, early fall of 2016, with over 60,000 acres burned. And that's in western North Carolina alone. So there was other fires in that region. So it is a fire area. It's an area that experiences fire, but that often gets drowned out by other events that happen in other parts of the country. And so this kind of reawakened interest in, okay, there's fire in eastern systems as well, and how do we work with that? So again, this concept of fire suppression, we've moved away from it, but I think this set of figures really illustrates the impact of fire suppression and what the aftermath of that we have to deal with today, and we'll have to continue to deal with for quite a while in the future. So this particular photo pair is from the Bitterroot National Forest, and it's the same house in both pictures, and the one from 1871, so typical of the mid-19th century, you had regularly occurring low-intensity surface fire and an open forest dominated by fire-adapted ponderosa pine. So ponderosa pine, again, doesn't have a lot of branches low. Typically in those areas, it's almost described as a parkland. It's open. You can like ride your horse through it. And fire basically acts as a vacuum cleaner through that area and just cleans up all the debris that might fall down. Through fire suppression, however, by the late 20th century, we have dense thickets of fire-intolerant species, incense cedar, other pines coming in. So we have predisposition to forest infestations, qualities of disease, and higher intensity fire, because now you have a fire that can spread from the surface on into the canopy, and that's really what becomes our most devastating fires. And the other thing that we have that's acting on the landscape now that's more of a modern issue that we have to deal with is, again, the WUI, the wildlife-urban interface, and how we work with fire in those communities. Gatlinburg brought that to light, so did the Thomas Fire, the other fires that occurred in California this past fall with devastating results and tremendous loss of life as well. But the reality is we have people living in areas that are fire adapted. They will experience fire. Especially in California, we've got chaparral areas. Those are fire-adapted ecosystems, and there's no way you're going to be able to put that out, nor do we realize now that we want to. But how do we work with those communities to make them more robust against fire? There's a program out there called FireWise that guides people to building communities and designing communities so that they are better able to handle fire. It can go from building materials to landscaping around your house, to even how you design the road network within your community. If you only have a system of cul-de-sacs, more and more fire chiefs out west are going to say, I'm not sending my crew in there because they only have one way in and one way out. So this is a community level. You cannot certify your own individual house as FireWise. It has to be done by community, similar to inoculation and herd mentality. If only one person does it, it doesn't really do any good. But if a community does, it can have that impact. But this has also led, from a geospatial perspective, to a real desire to have good depictions, good maps of that wildlife-urban interface. And that can be a challenge to map, especially in areas that are less dense, where you still have a lot of tree cover, but there's still that residential component that's coming in. So there's a fair amount of effort within the USGS and within our, not directly our program, but with partners that we work with, to get a better depiction of what that landscape looks like. A lot of what we do through the NLCD program, the National Land Cover Database, is to look at what we call impervious surfaces. Use that as our marker for how much built-up area is within a given region, and be able to kind of say how fire might behave. We also have developed a system of fuels classes that deal specifically with urban areas or suburban areas, and we call them burnable urban, because that's essentially what they are. Just as frame of reference, because I'll probably use some of these terms throughout the talk, there are typically 3 different types of fire. When we talk about fire in the landscape in a wildfire context, we've got a ground fire, which is depicted here. That is literally basically in the ground. You're burning up the needles and the duff and the leaves that are down on the ground, and it's burning that material. You have a surface fire, which is basically burning the twigs that are lying atop that, maybe into some of the lower branches that hang down, or shrubbery, and then you've got the canopy fires. And those are the ones that make the evening news. Those are the ones that are devastating. Those are the ones that really cause loss of life. I've been on plots where surface fires like that have been occurring in Alaska, and they move so slowly that we just basically just did our plot inventory while the fire was burning through the plot, and you just step over the fire and step back. So this is the type of fire, when we're talking about reintroducing fire in the landscape, this is what we're talking about. We're not talking about that. That's what we want to avoid, except in some rare occasions. There are forest types, there are ecosystems where even historically the fire that they've experienced has been stand replacing. So they will experience those more devastating fires, but not usually over the acreages that we're seeing now. So basically, what is our role, USGS's EROS role in fire science? And among other things, what we're trying to do is identify areas where fires have occurred in the past, estimate how severe those fires have been, provide information for predicting fire behavior, that's a big one for us, and then provide information for predicting fire danger, so the potential of fire occurring in the landscape in the near future. I'm going to touch on some of the products now that we develop in support of those, not all of them, there's a whole slew. I also want to say we're only a small part of the USGS in general, so there's other activities that's being done beyond EROS, but we try to collaborate with them as much as we possibly can. So from our perspective, the utility of the geospatial data that we can provide, and what we do at EROS is really done at a national scale. As we're looking at characterizing the landscape composition comprehensively over large areas, really regional to national scale. That's a big driver for what we do. And the thrust behind that is to do that consistently, so that we have consistent data wall to wall that will enable comparisons. If we don't have that consistency, then it's hard to kind of compare apples to apples. You're comparing apples to oranges or whatnot, and it's kind of hard to look at trends either spatially or temporally if you don't have that data consistency. So we're also looking at not only mapping things nationally in the current, but also going into the past. So we rely very heavily on that Landsat data archive, and so a lot of what we do kind of spans back to about '84, where we're looking and kind of bringing those data that we can do comparisons both regionally, spatially, but also temporally. And then that helps us understand trends that are going on and potentially link that to other factors that might be driving fire. And that could be climatological, but it can also be human and management decisions as to what's going on. So looking at fire science now specifically at EROS, we do have one slight challenge. Well, at EROS we have a couple, but USGS in general, we have one of our challenges is that we're not a land management agency. We're considered the science branch of the Department of Interior, the DOI. I don't always like saying that because that kind of implies that the other branches don't do science. They do, but we are really designated as the science branch, but we don't manage any lands. We don't, unlike the BLM or the Park Service or Fish and Wildlife, we don't own any lands that we manage. So anything we do has to be in partnership with other people and land managers. So we already are missing kind of that critical link between science, R&D, and the management side. And we're trying to overcome that, but it's definitely, there's definitely a barrier there. We have several projects, and I'll go into some of them, that involve our staff, our team at EROS, mostly mapping vegetation and fuel, but also monitoring burn severity and doing a little bit of predicting for fire danger. I'll start off with the burn severity part of it, and the products that we generate there. One thing that is consistent throughout, but in particular with the burn severity, is always this ground observation component. We do a lot of remote sensing. Again, that's our bread and butter at EROS. But within the fire science team, there's a big draw to connect that to observations on the ground so that we can always link back to the managers and say, okay, this is what you're seeing, this is what we're seeing, and here's how it all comes together. And this is why we can defend and justify the products that we're seeing and recommend that you use them. So in this particular case, we're looking at a burn severity plot where they're collecting CBI, or composite burn index data, to kind of use that as ground truth for some of the burn severity products that are generated from the Landsat data. And so we have the monitoring from above. And this again is basically just a burn scar map from Landsat, and where you can just really see that fire shine through. But we need more than that. We want to know more than just where has the fire occurred. We want to learn a little bit more about, say, the severity. And in order to do that, we really utilize the normalized burn ratio. Again, this is Landsat driven, so we're looking at Landsat bands 4 and 7, and ratios of that to really kind of highlight and draw upon this difference between healthy vegetation and burned areas, and use that to kind of identify not only that the area has burned, but how severely has it burned, because that's the other question that we want to get to. Our flagship program for that particular effort is called the Monitoring Trends in Burn Severity, or MTBS. I've talked to a couple people here today who use and utilize some of that data. And that one provides consistent information about the location, extent, and magnitude of burn severity for all lands in the U.S. There's a little bit of an asterisk associated with that because we do have size cutoffs for the fires that we map. East of the Mississippi, it's 500 acres or greater. West of the Mississippi, it's 1,000 acres or greater. So we don't map the really small fires. We are going back and looking at our historical record right now, seeing if there's any fires we've missed. Some fires were deemed unmappable in the past just due to data access issues that are now overcome with our free and open archive of Landsat data. And so we're looking at rounding that out. And that's a partnership between our team at the USGS, but also the Forest Service at GTAC down in Salt Lake City. And again, we basically leverage that DNBR, so we have a pre-fire image, a post-fire image, calculate the NBR ratio for each of those, difference those, and essentially the differences are then plotted in a histogram like this. And this is kind of where science meets art, because an analyst will look at this and use local knowledge where they have it, and kind of try to come up with these breaks where we're going to say, okay, anything above this threshold I'm going to label a severe fire. Anything in this middle category I'm going to call a moderate fire or a non-severe fire or unburned. And in some cases I've experienced growth here. I mean, any type of fire you can see here, it doesn't burn with the same severity everywhere. You're always going to have islands in that, and so the challenge is identifying where those occur. And again, this goes back to our list that I showed earlier about the number of fires that we had in the total acres burned. You could have a very high number of acres burned, but if they're all low to moderate fire, is that going to be as severe a fire year as a year where you might have had fewer acres burned, but they were all severe? One thing that the MTBS data does not account for is management activities on the landscape. So there's an effort underway right now to link the MTBS data, which is purely driven by remote sensing data, to management information that's contributed by the land management agencies. So I can say, okay, this fire might not have grown to be that big, but that was because there was a suppression effort put there. And even though we're trying to eliminate suppression on the landscape or reduce it, we're not trying to eliminate it completely. There are areas, if there's homes involved, if there's lives involved, certainly we're going to go out and put out the fire. But there are more fire use, we call fire use fires, where they are, okay, we're going to let it burn. It's in a wild area. Nobody's going to get hurt. We'll just let it go. So that information is not associated with this. So anybody who's monitoring trends needs to look at and account for that part of it too. What is the human action that went along with these? Similar to MTBS, using the same type of tools but with a slightly different bend, is what we call the Burned Area Reflectance Classification, or BARC maps. And these maps are generated immediately post-fire, sometimes while the smoke is still on and we've still got smoldering embers throughout the fire scar. And this is to support BEAR teams. These are Burned Area Emergency Response Teams. They go out right after the fire is put out, and they do assessments to see if there's any mitigation that needs to be done to keep other things from happening. For example, if you have an area on a high slope where the fire's gone through, and do we now need to go through and see, okay, if we have a significant rain event, is this area prone to landslides? And then go in and potentially do things to, if there is a high likelihood for landslide activity, go in and mitigate that. And that goes right into our debris flow modeling. So we do post-fire risk assessment of debris flow potential, and it's based on both the burn severity and also hydraulic parameters of that area. But these are only done when requested. This isn't done for any fire that occurs, but those that are high risk. And they basically take I forget what it is, but they have a cutoff in terms of a rainfall event and model that over the area, and if that then triggers debris flow, then they'll issue warnings for that area. For this work, we're looking at some directions to go to in the future. As I said, we're very, very much based on Landsat right now. We do want that to change, realizing what data we have available to us right now. Some of that is integration of other data sources such as Sentinel-2, and that work has already started. But we also want to look at leveraging structure information available through tools such as lidar or radar, and that will really give us more of a structural or physical idea of what's happening on the ground, not just the reflectance data. The reflectance data gets us a lot of information, but it does not tell the whole story. So we're looking at kind of comparing pre and post structure after a fire's gone through to say, what is the mortality, how much has been consumed, how has that arrangement of structure changed now that a fire has gone through, and what does that mean for the future? So that's really post-fire activities after a fire has gone through, but we also do a lot of work that's geared towards mapping vegetation and fuels, which is vital for pre-fire activity, so before a fire goes through an area. And these data products are used for a variety of applications. Certainly fire management decision support, how we're just going to look at fire in general on the landscape. Very much for fire behavior modeling. In fact, that component alone drives a lot of what we do, and what our major project called LANDFIRE is really governed by, is this fire behavior modeling concept. And fire behavior modeling is used both tactically and strategically. By tactical, we mean that is an active fire that is burning, and there's fire behavior analysts who are using the data to actually predict how that particular fire is going to behave. The strategic part of it is more, okay, it's the off season, I'm a land manager, and I want to see, okay, where do I want to put in treatments? And I do hypotheticals with the fire behaviors, but I use that same base data to see, okay, how is it going to behave? If I switch wind conditions, weather conditions, how's my fire going to behave? And how does that lead me to make good decisions about where to put treatments in on my landscape, or to let it be? So our main work with vegetation and fuels is under the umbrella of this project called LANDFIRE. Has various objectives, but basically it's to assess the vegetation, fuel, and ecosystem conditions on a national scale. National consistency has been a driver of that program since it started in about 2003, 2004. Has a variety of intended applications, but a lot of that is driven by fire. Not all of it, though. There are people who use it beyond the fire community, but that is our main driver. Overall, we have a suite of 30 plus or 25 plus products that are generated at 30 meter spatial resolution. Again, this is driven by Landsat. And we're looking at vegetation type, structure, and succession, fuels, both surface and canopy, and then fire regime. So what is the expected fire behavior in a particular plot of land, and how is that departed from the historical fire regime? That's another part and component of that. LANDFIRE, again, as I said, is very much driven by the Landsat imagery, and the other data source that we really rely on strongly is field data. We have right now a reference database that contains over 1 million plots for the entire country. We rely very heavily on the Forest Inventory and Analysis Program for forested systems, but we use an agglomeration from all sorts of other federal agencies, local agencies, universities, what have you. As one colleague put it, we're little data ferrets. We'll take anything that's available and consume it. Pretty much the way we get from data to maps is using decision trees. Either random, we've used random forest. What we've basically used right now is, C5 is just another tool. But basically using that plot information to drill down into any type of spatial data. We use Landsat data. We also use elevation data and some other ancillary data sets to kind of build these decision trees and then apply them at regional subsets of the entire country. Don't map the entire country at once, but we block it down into basically ecologically meaningful units and then map along those scales. Our initial base map represented the 2001 era. It was informed by a collection of field reference data, Landsat imagery, biophysical gradients, and other ancillary data sources. And again, we relied, just as we do now, on classification and regression tree techniques. Since then, we realized one-shot deal isn't really going to help us much. If 2001 is now 2016, we need to update that data to keep it current. So since the initial inception, there have been several updates to that data, first bringing it up to about 2008, and then after 2008, we have updates that represent about every 2 years. We go through 2014. You'll see we don't have 2016 on here. That's because right now we're in the middle of an actual remap. We're not just making minor changes to the maps as we do in our update process. We're actually mapping the whole country from scratch again, using new Landsat data, additional plot data, new models, techniques, trying to address some of the feedback that we got from our users and fix things and just bring things up to current. And that's what we're trying to make one of our hallmarks is being responsive to user feedback. And here's just one example, was a desire for greater fidelity in our forest height product. The example I show here is Alaska, which was particularly egregious in our first product that came out from the 2001 era, where we had 2 classes. It was less than 10 meters or greater than 10 meters. That was it. That was all we could do at that time that we felt comfortable with. So we went through some effort to bring it at least up to our standard that we had for the contiguous US, which is the legend that you see listed there, which has its own issues, but at least it's not a two-class classification. And we did that by integrating Spaceborne lidar data from the ISTAT glass mission. That gave us, I think overall, 60,000 usable observations throughout the state of Alaska. And so we were able to really build decent models off of that. We basically use that in lieu of field data, which is very lacking in Alaska, especially interior Alaska. And that really helped us drive that mapping forward. We've continued along that thought. Height continues to be one item that we get a lot of feedback about. And one of the things we want to do is see how can we integrate, how can we show that LIDAR data, including airborne LIDAR data, in our mapping process will get us the products that we need and that our users have been asking for. So we had a little side project that was funded through NASA to develop this tool called Chislik. And we basically wanted to provide a tool that would allow people to update the LANDFIRE products with LIDAR data if they had it available. But this is a nice demonstration of, this is from an area in Colorado. This is the original LANDFIRE product with its gross level bins. And most of this area looks like it falls into the 20 to 25 meter category. This is that same area mapped with LIDAR, but you have continuous canopy height, which is much more representative of the heterogeneity in the landscape. And that heterogeneity is important to fire behavior. It really impacts how the fire is going to behave. So that's something we want to capture. But what we also wanted to show in the bar chart that you have here, that is the representation of the pixels from this map, and the curve is the representation of pixels from that map. And what's nice to see is that LANDFIRE data just aren't necessarily wrong, they just don't have the resolution that we want to have. So for our ongoing remap effort, we are incorporating airborne LIDAR data where we have it. We're leveraging it. We realize we don't have that data wall to wall. We've had to deal with that fact by using it basically as training data within other models, because what we can't have is what we call a Frankenstein map, where we've got bits and pieces that are mapped to this level and other pieces mapped at a different level, because then we don't have that data consistency that we've been harping on for the last 10 years in this project. But we have moved from our general classification that we had here to now we are going to produce heights continuously and allow end users to bin them as they see fit. There's a certain error associated with that we need to quantify and definitely spell out to end users, but it gives them more flexibility in what they want to do. Another component of what we do in LANDFIRE, but also in terms of research at EROS, is looking at wildland fuels in general. And part of our challenge is understanding the understory fuels. A lot of what we talked about structurally before, that's the upper canopy. And in a way, that's an easier thing to quantify. Now we're looking at below the canopy and what's going on there and how to tease that apart and the tools that we need and the data we need to do that. So we've had a little project going on in Superior National Forest where they've had an issue with balsam fir encroachment. Balsam fir occurs naturally up there. It's part of the systems, but it is spreading. It's growing in areas where it hasn't grown in the past. And that's a significant issue for them because balsam fir is a ladder fuel. You can see a little example of it in the photo, but it's got branches that sweep low to the ground, and it stays that way even as the tree grows. So it's very flammable. It's also susceptible to disease, so you have a lot of dead standing there as well. And they just don't have a good idea of where this balsam fir is occurring. And we teamed up with a couple of other projects that were going on up there to get them an estimate of, okay, where's some of this balsam fir growing in the understory. So I skip over that, but this just kind of illustrates, the levels and the density. I mean, some people don't think that the forests up north there get as dense as they do, but they can be pretty tricky to get around. And they do experience a fair amount of fire, even historically. There's some pretty big fires there. And gosh, I think it was the mid to late 90s, they had the big blowdown event that decimated thousands of acres up there as well. So this is in the Boundary Waters area, roughly, for people who've been up in that area and are familiar with it. So again, we're leveraging the LIDAR data. The state of Minnesota has basically flown the entire state, so it's great. It's available through their DNR. The data density isn't as great as in some places where they've collected the data for vegetation analyses, but it still gets us, I think, what we need. At least it's a good starting point. So we use the data from the point cloud to kind of start teasing apart what might be happening down in that lower level of the canopy. And we've had a student intern with us for the last few years who's delved into this and generated, I don't know how many metrics from the LIDAR data, but a fair slew of them, and kind of used those as a starting point in just a series of regression trees and just linear regressions to see what will fit best to observed conditions on the ground, and what will give us some estimate of the canopy cover in the understory. We have plot data to go along with this, measured those on a point line intercept and rounded those up. And he ran a whole, as I said, a whole series of metrics, but then also a whole series of regression analyses to kind of tease apart what might be useful and what isn't. And he's had mixed success, but we've plotted and mapped the data that he's been able to work with and generate, and we're getting results that are promising. When we align this with other data sources that we do have available, in this case the reds indicate areas of higher balsam fir amounts than others, trends agree. So we're not necessarily very confident in the absolute numbers that we have right here, but we are confident in the relative numbers. So if we're saying it's low, it's probably low. If we're saying it's high, it's probably high. And that agrees with some of the feedback that we've had from Superior National Forest as well. We're hoping in the near future, hopefully this summer, to go back up there and collect more data. We also want to do some terrestrial LIDAR scanning and kind of bring all those data sets in together and to bear and to do some more validation work up there. But that's really one of the next steps that we're looking at following. A lot of the fuels information also feeds into smoke modeling. That's something we don't do a lot of there, but our LANDFIRE products, especially our fuels products, feed into this system or this framework called Blue Sky that's used for smoke modeling and emissions modeling. That's housed by the Forest Service, and we work closely with them to kind of keep those data up to date and going. And then you can use that to provide real-time products, but also custom modeling scenarios. But this is a growing area of interest due to health concerns, air quality, that kind of thing. It's also a major concern because this is something that keeps people from accepting fire on their landscapes, not only because of health, but just it's impractical. People don't like it. And so when we're trying to convince people to do prescribed burning in their area, having a good understanding of what the smoke potential is really important, so we don't do it on really particularly bad days. And just one little example from basically linking our management and our science aspect. This was in Grand Canyon National Park. They had flown LIDAR data, I think in 2012, but they didn't have anybody on board on their staff to actually work with the data, and we happened to link up with one of their fire ecologists, and so we'd be more than willing to. And their particular scenario was that they are prime territory for Mexican spotted owl nesting and roosting habitat, and the spotted owl is a federally protected species, so they have to protect that habitat. Now at the same time, they also are mandated to manage fuel loads, and they do a lot of prescribed burning. They have a very active prescribed burning program in that park. So what they really wanted to know was, where is this habitat, and we need to know it pretty specifically because we can't burn within that habitat, or at least not without a lot of headaches and a lot of additional permissions. So we worked with them to get some of the information that they wanted, and it turns out that the spotted owl habitat links very nicely with things such as large tree density, basal area, variation in canopy height, and just other structural parameters like that canopy cover. So things that lend themselves very well to getting from LIDAR data, which is what they wanted to do. So this is our study area. So this is the entire park boundary in yellow where we actually worked. This is the North Kaibab Plateau. This is the national park portion of it. So this is the north rim of the Grand Canyon for those people who are familiar with it. And then this is the Kaibab National Forest. And they work very closely with each other. There's good cross-boundary cooperation between the two agencies right there. So we used those data, and basically because they were looking at really wanting to identify metrics that related to individual trees, went in and just basically generated an algorithm to find high spots within the canopy, or within the canopy height model from the LIDAR data, identify those as tree stems. There's a considerable amount of cleaning up that needs to go in with that, but then related field data that we had in terms of height and DBH to link that back and essentially generate a pseudo tree list with heights driven from the LIDAR data and then modeled DBHs associated with that, so we could get at basal area And their large tree cutoffs were all based off of DBH measurements. And the results we generated they've been very happy with. They found in particular the canopy cover product that we generated was something that they've used quite a bit. Just as an aside, that area was an escaped prescribed fire, which is still shining through. And the other element that we did was, so count density, so this is a count of large trees, is something that they found very beneficial. And then we kind of just, Simpson's reciprocal index, related to people who are familiar with like Shannon's diversity index or Simpson's diversity. So this is something similar to that, only we were looking at the distribution of lidar returns within the canopy by density layers, kind of using that as a way to estimate, okay, how complex or how multi-storied is that canopy in a given location. And then finally, moving forward, one thing that we want to do is keep looking at other missions that are coming up. And one aspect from our drive to be a national system and nationally consistent, and yet still integrating LIDAR data, is this interest in the future Spaceborne missions that are coming up. JEDI and ISAT-2 are the two that are really looming on the horizon, with ISAT-2 launching this fall and JEDI not too long after that. Though JEDI is going to be on the International Space Station, not a separate launch per se. So the data here are really more analogous to the JEDI data because they're waveforms. But again, this kind of gets at what we would like to see in terms of, particularly, say, again, ladder fuels and that fuel load within a given area. So here we have pretty much consistent vegetation distribution from the top of the canopy on down to the surface, versus here we have what we call a sub-canopy airspace, or a gap. And that could allow us to determine, is this an area where we're going to have, where we've had fuels build up and where we need to go in and do some type of treatment, whether it's a prescribed burn, thinning, that kind of thing, mechanical remove. These data, of course, are not going to be wall-to-wall. They're sampling data, both of them. But again, for us, the nice part is that they're going to be nationally consistent. We'll have data for the entire country. I guess with the exception that JEDI is not going to have data from Alaska, but still, for CONUS, we'll be in really good shape. And this just kind of sums up that last point. Again, integrating what we're really interested in, integrating that local scale, that field component, that understanding what's happening very local at a point, to a regional scale, kind of relating that to other data that we have, and then building products that people can actually use to make the decisions that they need to in order to effectively manage to manage fire on our landscapes. And I think that was the last one.
All right, so we have time for questions.
Thank you, that was great. I was wondering if you had unlimited money and staff and no constraints like that, what products would you make, new products would you make for monitoring the wildland urban interface? What would you want to know about fire?
That's a really good question. I think for us, the key thing would be being able to drill down and, because we're really interested in looking at what would be burnable in that area and how would fire behave. So it's really probably getting at a finer scale resolution, and that's one area where we've talked about maybe going down to aerial photography to really carefully delineate what exactly is going on, because the placement really almost of individual houses is critical, and that's not something you can resolve with Landsat. It's just, we're just a level too big for that. So that will allow us to quantify that ratio of non-permeable but also non-burnable surfaces with material that can burn, with a caveat, and this is the part where this is the part that's going to be harder to do through remote sensing, but it would be nice to link in, is information about let me think. Essentially the building materials, because the houses do burn. Some are just more likely to burn than others, depending on what they're built out of. So they essentially become fuel as well. We tend not to want to think of them that way because we think of them as the item that needs to be preserved. But in all reality, depending on what the home is built out of, it is going to contribute to the fire spreading or it's not. So when we talk about our burnable urban, we're not just always talking about the vegetation component, although that's the main part. But then that also allows us, a lot of communities only have limited funds to put in, or land management agencies, I should say, only have limited funds to put in treatments. So a lot of those treatments are put in close to residential areas or to those high-risk areas because that's where it's really going to have the biggest bang for the buck and where you can justify that. So being able to monitor those over time, again, at a finer resolution, I think is something that we could really, really benefit from. The unfortunate kick side of that is that a lot of people who live in those areas don't want to see the treatments go in because they see them as ugly and detrimental. So being able to monitor how effective those treatments are, if we do lower impact ones, I mean, one thing that's really big right now is goats. People don't mind goats clamoring around their backyard, apparently, and they'll eat a lot of stuff, and they'll eat a lot of that low stuff. I'm not kidding. I mean, goats have become a big thing. But they're not seen as ugly. You know, it's kind of cute, I think, for a while. I think after a while the goats get on your nerves, too. But that's, you know, that's the kind of thing that we really need to be able to monitor. And I think where we've really been, and that's a big we, I think in the fire science community in general and fire management in general, have been really bad about communicating with the public. We've not been as effective as we can be. And to have visuals to tell that story, I mean, they say, you know, picture's worth 1,000 words. And I think in that particular case, that's really true. So anything we can do to highlight the impact that the decisions are having on people's lives is something that we really need to look at.
So I have a question about the LANDFIRE.
Uh-huh.
You said something about a new method being used for 2016. I was wondering about the land cover legend. Is it going to change from the 2001?
Yes.
Okay.
However, what we have done, or what has been done, and there have been changes overall for on two fronts. One is there's the actual EVT legend, the vegetation type legend. We have collapsed some classes together. Some new ones have been added in. You are going to see a lot of it's going to stay the same. We're still using the ecological systems. So a lot of it will be over one-to-one. It'll be the exact same thing. But there has been a collapsing of some systems into one, and then there's been some that have been broken out due to feedback. Those tend to be regional. At the same time, there's the EVT, what we're calling EVT fuels. So there's there we've been trying to stay more consistent with the legend over time because if we don't, that really messes up people with their fuel modeling. So the changes don't necessarily translate all the way through all the products. But the actual vegetation type product, you are going to see some changes in the legend. But it's not a dramatically new, it's not like we're going from ecological systems.
In follow-up on that, there was one slide you showed in Alaska where you actually looked like you had a legend that was like a combination of continuous canopy height or something and then categories. Is that going to be available in that newer version?
I went past it. I know which slide you're talking about. We had in our existing, there was one. We are going to be, this one? That one.
Yeah, wait. Yeah, that one.
That one. Okay, so this is now for CONUS, so for the contiguous US, we have shifted from this legend to doing a continuous legend for height, and for canopy, both.
Okay.
So this is the original. This is what you're going to see through all the update products up through 2014. There is a question. We might be doing an update 2016. We might not, depending on how long the remap effort takes. But all the remap products are going to have the continuous legend for structure.
How about carbon? Later.
Maybe someday.
So you talk about MTVS, you're not able to assign suppression efforts, to the polygons. Is there any plans to do so? And I wonder if you couldn't detect suppression efforts by just looking at the shape of the fire boundary.
You definitely could. If you wanted to do, you could basically, I think you could on fires, as you're right, if you've got this linear feature coming in or it's aligning with a road or something like that, definitely you could start seeing, okay, there's definitely some activity that went on here. To answer your first question, is there an effort to link that information together? Yes, there is. One of my colleagues actually put in a CDI proposal. That's how Nick and I first got linked up, was through another proposal through our Center for Data Integration that's sponsored by the USGS. So they are looking at taking information available from land management units and linking that with individual fires, so people could go into one database and say, okay, this area experienced a lot of big fires, but this area didn't. What, and before you reach a lot of erroneous conclusions, you can go, well, because this area has a active fire suppression program and this area doesn't. So that's what we're trying to add that information as part of the MTBS and under the MTBS umbrella. So we're not going to create something new. If that does happen, it's going to go under the MTBS house or umbrella, basically.
Awesome.
Yeah.
I got a bunch of questions, but I'll only ask one. Thinking of kind of not necessarily prioritizing, but insurance companies. Got to be this is of interest to them, especially while they have the interface. Do you know if there's any efforts for EROS, DOI, USGS to say, hey, why don't you help us help you? Let's move into an endeavor to map wildland interface together.
The insurance question is definitely something that is becoming very prominent in that context in particular. What they draw upon very much is insurance requirements for people who live in flood-prone areas, especially coastal areas. You're required to carry additional insurance on your home, and also linked to mortgages and such. And they're looking at potentially doing something similar for people in fire-prone areas. There hasn't been a direct outreach between the two groups, whether it's DOI or other federal agencies and the insurance companies, as far as I know. I really think that there would probably be, on behalf of the government, be really leery to do that just because of fear of lawsuit or anything like that geared to it. If they say, hey, if somebody says, no, you're in a low-prone area, and then something happens, I mean, we've already seen that happen when we do other mapping components. And I'm wondering if that's one thing that might be keeping people from actively working in that arena. But it is something. The insurance question is something I've heard mentioned over and over again in terms of.
We ultimately pay for it.
Yeah.
Every year.
Yep. Absolutely.
Same as with the flood plan.
Yep. Absolutely. There is more. One thing that is having an impact, not surprisingly, is when new communities are going in and people are seeing how they're developed and they're bringing in the local fire chiefs and them going in and saying, we're not going to come in here. We're not, because it's not worth the risk to our life, and it's also resources going to something that's essentially not going to be savable when we could be going over here where people have built more wisely for the area and where we have a higher probability of actually being able to be effective. That is having an impact.
Any more questions? I think this will be our last.
How open is the source code for something such as Blue Sky?
That Blue Sky, I would have to, that I can't tell you off that, I don't know.
Or even the feature of using point cloud data to represent the canopies?
A lot of that we're doing, and anything that we do, we're trying to make such that we're putting it out there, and even though it's not necessarily open, the lidar processing we do is all done through LAS tools, which is proprietary.